what is wind? So wind is defined as the horizontal movement of air. In this video series, we're going to get in detail about wind on a big scale, on an upper level scale, lower close to the surface scale, and also different local wind patterns. This all goes back to how temperature affects pressure. So this is an image that we've seen before when we were talking about the atmosphere. Recall previously, we talked about how the troposphere is the closest layer to the Earth. Right here is our troposphere in this dark blue color. And we notice that it's higher at the equator and it's lower at the poles. Also recall, what is the name of the dividing line between the troposphere and the stratosphere? If you said the tropopause, you are right. So the tropopause height is going to vary. We kind of talked about this before, but what we notice at the equator, that tropopause height is higher than it is at the poles. Also, it is warmer at the equator. We've talked about how the Earth is on a tilt, but we have the sun shining primarily around the region of the equator at the closest to 90 degrees angle. It varies on what day of the year, but the sun does not hit polar areas right at 90 degrees, obviously, so these areas tend to remain colder, which causes our troposphere and our tropopause to be shorter at the poles and larger at the equator. So hot air forms basically what can be thought of as a bubble, and it creates what we call pressure levels, which our altimeters actually follow. Now, higher temperatures equals a higher tropopause. The reason being because, as I just mentioned, hot air is naturally expanded. It's bigger than colder, denser air. With hotter air, a given pressure level is going to be found at a higher altitude. And we're going to be talking about why here and how that works in a minute. First, let's just take a look at this column of air. So here we have an air column, and we are going to pretend for the purposes of my first example that this air column has got a fixed number of molecules in it. This is not like real life, but we're going to just start here. Okay, so here you have an air column. It's sitting there in a city. It has a fixed number of molecules inside that air column. Here is the same air column, like I mentioned. It has a fixed amount of molecules in it. So we have city A and we have city B, and we have two different air columns. Currently, they are both at the same temperature. Both of these cities are at the same exact temperature. They're also at the same pressure at the surface because since these air columns have the same amount of temperature in them, they have the same amount of pressure, so they are identical. If city number 1 gets colder, then what happens to that air column? Okay, we've talked about how heated air is going to expand and cooled air is going to condense or contract. So if we have a fixed number of molecules in our air column in the city that gets colder, you notice that that air column shrinks. It's not as tall because that air has gotten colder and it's contracted in size. In city number 2, we have a larger column going on because that air, remember we were pretending it's a fixed amount of molecules in that column, that air has expanded. The air molecules are farther apart. However, because we have the same amount of molecules in these two columns, we are finding that they each have the same pressure actually at the surface. Okay, but city number 2, the air column got a lot taller and it's still exerting the same amount of pressure. Now, let's talk about what's happening aloft here. So at the cold column, all right, remember at the surface, initially the pressure was the same. But what happens as our air columns have expanded? So here I have in city number 1, I've got a lower pressure aloft. It's because there's hardly any air molecules sitting on top of that pressure. In city number 2, we form a higher pressure aloft because there's a lot more air molecules that are exerting some pressure here aloft. So we have a high pressure. Now, we have talked about how air naturally uses something called pressure gradient force, which we're going to talk about here in this video series. That makes air naturally flow from a high pressure to a low pressure. So when it does that, moving from a high pressure to a low pressure, it is horizontal movement of air, ergo wind. So if we take a look at what's going to happen in the sea level of my situation here, we have some air molecules leaving this column of air, leaving the high pressure, flowing over here into the low pressure. By definition, air flows out from a high and into a low. And because of that, we're going to add some air molecules to column number 1, and the surface pressure is going to rise. In city number 2, some of these air molecules left because of our high pressure aloft, and we see the surface pressure actually falls a little bit. Okay. Now, all this is great. However, you're probably thinking, well, there's not a fixed amount of molecules in a column of air. You are correct. That was just for this example to talk about high pressure and low pressure flow. Okay, so let's now say we have unlimited amount of molecules. We don't have a fixed number of molecules anymore in the column of air. If we have a colder column of air and we have a warmer column of air, they don't have a fixed number of molecules inside them anymore at this point. Which of these columns of air would you expect to have a higher atmospheric pressure at the surface? Now, think about this. In that colder column of air, how close are the molecules together than the warmer column? They're closer together, right? They can get more densely packed together. They're not moving, they're not bouncing around. They're just like, shivering cold. Well, that tells us that our cold column of air can have a higher pressure at the surface than the warmer column of air. A lot more molecules are sitting on top of my column, pressing down at the surface. In a previous video series, we talked about standard day. We talked about how standard atmospheric pressure, if we had a 1-inch column of air that went up unlimited and it was a 1 inch by 1 inch, it was going to weigh 14.7 pounds per square inch. That's our standard pressure. However, if that column of air got colder than standard, we get more air molecules in there and we can get a higher than 14.7 pounds per square inch. Or if that air got expanded more, we might have less molecules in that area. We're going to have a lower pressure. Okay, so that's important to realize going forward. Be aware that a colder column of air has a higher pressure at the surface than a warm column of air, if that column of air is permitted to have just however many molecules. All right, it doesn't have a fixed amount of molecules. Now, how does this have to do with our different pressure levels? Okay, so imagine with me that we have a given pressure, okay? We're going to keep talking about the standard day business here. So what is going to happen with a standard day is we would have a normal height at which we would find a certain level of pressure, okay? Usually pressures aloft are measured in hundreds of millibars. So in my picture here, if you take a look at this, in a standard atmosphere, and this is a little hard to see, but this is our level of the 500 millibar level. And just imagine this is 3D, we have kind of a box. This is standard at 5,640 meters high. That would be on a standard day. That's where we'd expect to find a 500 millibar pressure level, okay? In millibars on a standard day, we would actually find it to be 1013.2 millibars at the surface, okay? So at 500 millibars, that pressure has been lost. As we go up, that's generally going to be found at 5,640 meters. However, let's pretend the air is colder, okay? If that air is colder, that column of air is colder, it gets all condensed again. And what we find is that the level where we would find the 500 millibar pressure level, it decreases. In this example picture, it's decreased down to the 5,580 meter mark. Okay, so my column of air that was 500 millibars in pressure on a standard day, at this height, it's still 500 millibars in pressure. On a colder day, it shrunk. However, on a warmer day than standard, that column is going to rise higher than where it was on a standard day. So here's a warmer day than usual. That air expands, hot air expands, and we end up with the 500 millibar level up here. It's risen here, and now it's at the 5,700 meter mark. So it's kind of varied. When we think about a pressure level, we have to realize it's not at a constant altitude. It's not sitting there always at 5,640 meters. Sometimes that 500 millibar level goes up to 5,700 with a higher than normal pressure. Sometimes it goes down 5,580 meters at a lower than normal temperature. So that is why that pressure is going to vary in the height. Air expands to greater volume in warm air and shrinks to lesser volume in cold air. So wind is the result of all this. So I want to show you a dramatic video off YouTube. It's a couple minutes long. We're going to watch it here. 4 months after it opened, this happened at the Tacoma Narrows Bridge in Washington State. And resonance caused by the wind caused oscillations because of the aerodynamics of the bridge itself. I'm not going to show the whole video, but we're just going to kind of fast forward here.
On the heaving roadway, the 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick. Back out of the danger zone, all stricken spectators are driven to safety as the bridge gyrates like a nightmare high above the river, twisting, turning, curling. The lone motorist is forced to abandon the car. He has but a few minutes in which to save himself. Face to face with fate, his destiny hanging in the balance. Will he heed the last warning or perish with the doomed structure? But he saved himself by seconds. No structure of steel and concrete can stand such a strain. Steel girders buckle and giant cables snap like puny threads. There it goes!
So again, that was the Tacoma Narrows Bridge, collapsed in the 1940s, only 4 months after it actually opened. And the resonance caused by the wind caused the oscillations of that bridge just because of the bridge's aerodynamics. So we're going to continue our discussion about wind in the next video.